All right, so this is the think and solve for chapter 3. And it worked much better when I was doing this in writing, but I wanted to try to keep this just verbal. So, chapter number 35, you toss a ball straight up with an initial speed of 30 meters per second. How high does it go? How long is it in the air, ignoring air resistance? For the sake of this, let's just assume up is positive. So if up is positive, that means down is negative. The acceleration, once it leaves your hand, the only force acting on the ball is the force due to gravity. It's weight. The weight is acting downwards towards the center of the earth. Now, we're ignoring air resistance, as it does say in the problem. So the only force acting on it is the force of gravity downwards. Since the force is downwards, the acceleration is downwards. The acceleration would be the acceleration due to gravity, because that's the only force acting on it. Now, if the acceleration due to gravity, if this takes place on Earth, which we will assume, then the acceleration due to gravity is, taking the direction into account, negative 10 meters per second squared. Because again, we assumed up was positive, and therefore the acceleration is negative. So if it starts out at 30 meters per second, that means that after 1 second, it's now going 20 meters per second. Because acceleration, if the acceleration is negative 10 meters per second squared, that means the velocity changes negative 10 meters per second every second. So it starts at 30, we subtract 10 to get 20, subtract 10 more, so after 2 seconds it's going 10 meters per second. After 3 seconds it's going 0. That once it reaches the peak, it is now at 0 meters per second. That means it stops. For a brief moment it stops before it's turned. That's the point where it turns around. So it is in the air. If we go with 10 meters per second squared, it is in the air for 3 seconds before it stops and starts to turn around. So the question is, how long is it in the air? Well, 3 seconds to go up, 3 seconds to come down. How high does it go? Well, if we look at just the journey upwards, it starts at 30 meters per second, it ends at 0. So the average is 15. That's the middle. So I'm at 30, I'm at 0, the average is in the middle, 15. The average speed or velocity is 15 meters per second, and it does that over 3 seconds. It's traveling for 3 seconds up. So the distance to travel will be 45 meters. That's 15 meters per second times 3 seconds, which is 45 meters. Now, for 37, what is the instantaneous velocity of a free-falling object 10 seconds after it's released from a position of rest? What's the average velocity during this 10-second interval? So instead of using the 10 meters per second, let's use 9.8. For this problem, it's in free fall. Let's just assume down is positive. And so the acceleration, well, let's think about the forces. Once it's released, the only force acting on it is the force due to gravity. We are ignoring air resistance. He doesn't say that explicitly in this problem, but we have to, because then the problem becomes way too complicated. And that's even beyond the scope of the calculus-based course, if you want to do it right. So we have this object that's falling at so it starts at rest, so it starts at 0. After 1 second, it's going 10 meters per second, then 20 meters per second, 30 meters per second. Oh, sorry. That's if the acceleration is 10 meters per second squared. We're assuming 9.8 meters per second squared. Again, we're assuming it takes place on some average spot on Earth. So it starts at 0, then it's going 9.8 meters per second, 19.6 meters per second, 29.4 meters per second, and so on. So every second that ticks by, the velocity changes by 9.8 meters per second. We assume down was positive, and the thing is moving downwards. It starts at 0, so it plus 9.8 every single time. So after 10 seconds, it's going 98 meters per second. The question is, what's the average velocity? What's the instantaneous velocity? That's the 98 meters per second. The second one is, what is the average velocity? Well, the average velocity, well, I start at 0 and I get to 98. So the average between 0 and 98 is 49. 49 meters per second is the average over the 10 seconds. And so how far will it fall? Well, it's going an average of 49 meters per second for 10 seconds. You have multiply them, 49 times 10, 490 meters. It falls 490 meters. You could also use the equation on page 48, I believe it is, the 1/2 gt squared. That gets you the exact same answer. 38. Car takes 10 seconds to go from 0 to 25 meters per second at a constant acceleration. So now he's actually stating that the acceleration is constant. That is the assumption that we made for the plug and chug. If you wish to find the distance, use the formula. Then it gives you the 1/2 AT squared. What is the value of A? Let's see. If you wish to find, so the question is, he's just throwing that in so he could use it later potentially, or gives me an excuse to use it. But the question is just asking, what's the acceleration? I'm going from 0 to 25 meters per second, so my change in velocity, he doesn't give a direction, so we're talking about scalars here. My change in speed is 25 meters per second. That's final minus initial. That's 25 minus 0, which is 25. So 25 meters per second is my change over 10 seconds. My math is 25 divided by 10, which is 2.5. 2.5 meters per second, or 2.5 meters per second squared. That is the acceleration. Now, if we wanted to find the distance, we could then use that value of acceleration in there and the time of 10 seconds and whatever that ends up being. I guess so 2.5 divided by times 1/2 is 1.25 times 100, 125 meters. And then in 39, it's very similar, except, well, let's see, we're jumping 0.6 meters. I suggest we stick with the metric here. 0.6 meters straight up and asking for time. We assume G is 9.8 meters per second squared. And so if I said 0.6 is equal to 1/2 times 9.8 t squared, 1/2 times 9.8 is 4.9. So I now have 0.6 equals 4.9 t squared. I'm trying to isolate t, but first I have to isolate t squared. So I get rid of that 4.9 by dividing both sides by 4.9. So I get 0.6 over 4.9. And then whatever that is, that's equal to t squared. To get t by itself, I have to undo the squared, so I take the square root. So the square root of 0.6 divided by 4.9. Now, I haven't tracked units this time because I know I'm dealing with SI units. I dealt with meters. I dealt with meters per second squared for acceleration, meters for the displacement. And so time has to be in seconds. If the equation is valid, time is going to be in seconds. And the last one, 36, I want to talk about 36, even though it wasn't officially assigned. It does bring up a couple things here. I think emphasizes the velocity, change in velocity, a couple of the concepts that we've sort of danced around in terms of these problems. In 36, the ball is tossed with enough speed straight up so it is in the air for several seconds. We will assume more than 2. What is the velocity of the ball when it reaches the highest point? So a ball is thrown straight up. When it changes directions, if we assume up as positive, we could assume down as positive, but let's just assume up as positive. If we assume up as positive, it starts out with some positive velocity, and then at some point it has a negative velocity. Well, you can't go from positive to negative without going through 0, unless there's a rip in the space-time continuum. But assuming that there is no rip in the space-time continuum, that as it goes up, when it reaches the peak, that's 0, and then it starts coming back down. So that's A. B, what is the velocity 1 second before it reaches the highest point? Well, we can sort of work in reverse. If it's losing 9.8 meters per second every second, well, if it's at 0 at this point, then 1 second before it has to be going 9.8 meters per second, because it's going to lose 9.8 in the next second, and then it'll gain 9.8 in the next second, and then gain another 9.8. What is the change in velocity during this 1 second interval? So it starts at 9.8 meters per second. It ends at 0 meters per second. And so therefore, the change in velocity is final minus initial, 0 minus 9.8, or negative 9.8 meters per second. That is the change in velocity. What is the velocity 1 second after it reaches the highest point? Well, it's at 0, and the change in velocity is over time is the acceleration, which is negative 9.8 meters per second squared. So it's at 0, and then we subtract 9.8 again, so we're at negative 9.8. The negative 9.8 meters per second just means downwards. So it's going down. 1 second after it reaches the peak, it's going downwards. Should not be a shock. And then what's the change in velocity during this 1 second interval? Well, it starts at final minus initial. It starts at 0, ends at negative 9.8. And so my change is negative 9.8 minus 0, which is negative 9.8. It is the same acceleration, or same change in velocity. What is the change in velocity during the 2-second interval? Well, it was going 9.8, and then it goes negative 9.8. The change is negative 9.8 minus positive 9.8, which is negative 19.6. And then it asks for the acceleration. So during the first one, it goes from 9.8 to 0 in 1 second. So that's negative 9.8 meters per second divided by 1 second, which is negative 9.8 meters per second squared. Shocking. That's the acceleration due to gravity. Afterwards, it goes from 0 to negative 9.8 meters per second. The change in velocity was negative 9.8 meters per second divided by the time interval, 1 second, which is negative 9.8 meters per second squared. And then for the 2-second interval, it goes from positive 9.8 to negative 9.8 with a change in velocity of negative 19.6 meters per second. Over 2 seconds, negative 19.6 divided by 2, negative 9.8 meters per second squared. Yet again, the acceleration is constant. So, something to keep in mind.